Honors Chemistry, and welcome to picking up with 3.8 types of energy, right? So matter and energy go together in this chapter, like I said before, because once we start talking about types of matter and then we introduce the concept of change, most changes require either the input of energy to make the change happen, or the change releases energy, right? And so we need some way to talk about it, right? We need to know what the right vocabulary is to talk about it, and things like how to quantify it, how to measure it, things like that, right? So thinking about types of energy, right? So your book talks about it a little bit, right? And I've stolen this from someplace on the internet down here, right? But when we talk about energy, right, there are two broad categories of energy, where our broad categories are kinetic energy, right? So the energy of motion, right? And then potential energy. So energy that is tucked away, but we can access it when we need it, okay? So there's mechanical energy, there is electrical energy, the movement of electrons, which we take advantage of all day, every day, right? Thermal energy, so heat or vibration, right? Which we'll talk a little bit when we get to temperature, right? Radiant energy, sound energy. Potential energy, which we talk a lot about in chemistry, right? Chemical energy, right? Super important. And that is the energy stored in bonds. And let us be crystal clear here, okay? Energy stored in bonds can be confusing, right? So let's make sure we put some proper words here. So we always release energy, right, when bonds are formed. And let's be more broad, right? When attractions are formed, okay? We always release energy when attractions are formed, right? We always require energy when attractions are broken. So when we say that energy is stored in a bond, we do not mean that when we break the bond, energy comes out, like, I don't know, cracking up a piñata or something like that. No, not like that, okay? Other types of potential energy, nuclear energy, super important, obviously, especially depending on where you live in the United States. Gravitational energy, you know, most of us dig that. And elastic energy, which I think you talk at length about in physics class. All right. In chemistry class, we are most interested in chemical energy. We talk a lot about thermal energy. We reference electrical energy a little bit, and light energy. Yeah, that's pretty much it. All right. Oh my gosh, conversions. Who would have thought, right? So let's go ahead and do some of these. So yeah, you are just supposed to memorize those, right? But now this should be just really basic, and you're like, wow, this is so much easier now. So the complete combustion of a small wooden match produces approximately 512 calories of heat. How many kilojoules are produced, right? So obviously our given is 512 calories of heat, right? And we have to figure out what conversion factors fit there. One of the most confusing things, right, is this whole big C versus little c cals. So do make sure you pay attention to that, and make sure that your writing is so clear that I will know which kind of C you mean, right? But we know that in terms of relationships, let's see what we got. 1 little cal is equal to 4.184 joules, which then means that 10 to the third joules is equal to 1 kilojoule. And oh my gosh, look at that throwback to the last chapter. Yes, everything from chapter 2, fair game for the rest of the school year. I can't emphasize enough. You'll see slowly but surely as we go through, but that is truly the foundation for the whole year, right? And so calories cancel, joules cancel, we're left with kilojoules, and that's how we would solve that one. All right, Skill Builder Plus. We have our 2.75 times 10 to the 4th kilojoules, and we would like to convert that to calories, right? So it's literally 3.5 backwards, right? Where we would now take our kilojoules and convert them to joules first, and then we would then take our joules, 4.184 joules, and convert those to little cals, right? Joules cancel, kilojoules cancel, and we have solved Skill Builder Plus. Yes? All right, fantastic. All right. Then in terms of, so then now we get on to a little bit more terminology, right? Exothermic versus endothermic, right? Exo, like coming out, right? If we think of like an exoskeleton from biology, right? Outside, right? So exothermic reactions are ones where energy is released from the reactants, energy is released from the system to the surroundings, okay? Exothermic means energy is released from the system to the surroundings, okay? Endothermic means energy absorbed by the system from the surroundings, okay? Energy is absorbed by the system from the surroundings, okay? Now, the thing is that for every one of these processes, the point of view is really important, right? Because if we think about it, for any process where we say, oh, energy is released, well, it depends on what we define as the system and what we define as the surroundings, right? So the way that you word an answer is very, very important to whether or not your answer gets credit, right? Because it needs to be crystal clear that you understand first what point of view you are taking and then whether or not energy comes in or out, right? So for example, let's talk about ice water, right? So let's say we have a glass, right? And in my glass we have some liquid water, right? And then to my glass we add some ice cubes. Okay? And so this would be my solid H2O, right? So my liquid H2O has a temperature of approximately 25 degrees Celsius. My solid H2O has a temperature of about 0 degrees Celsius, okay? So then what that means, right, is that as these two things are hanging out together, right, energy is going from the liquid water into the ice, yes? Energy is going from the liquid water into the ice, which means that from the liquid water's point of view, this is a, right, exothermic process. For the liquid water, right, for the ice component, it is an endothermic process, yes, because they are taking in that energy, right? And note that as that happens, right, eventually they reach the same temperature, right? The temperature of this is going to go down as it gives away energy, right? Temperature of this is going to go up as it absorbs that energy until we reach thermal equilibrium, right? So point of view, very important, okay? All right, temperature versus heat. Here are some more equations you do need to know. There's also one that says degrees Fahrenheit equals 9/5 C plus 32, which is basically, that's just this reaction flipped around, right? 1.8 is 9/5, okay? One of the important things to note about the temperature scales, right, is that this conversion is really easy, right? All we're doing is shifting it, right? By simply adding 273.15, all we're doing is shifting our point of view, right? So if we take a look here, so your book has conveniently marked where water freezes and where water boils, right? And we understand, right, from just life things we know, right, is that is 100 degrees change in Celsius, right? There is a 100 degree spread from water freezing to water boiling. And it turns out that, for Kelvin, it's the same thing, right? There are 100 degrees between where water freezes and water boils, right? Which means that the size, right, if we look here, the size of a Celsius is the same as the size of a Kelvin, which is why the conversion is as simple as shifting the scale 273.15 degrees, okay? Kelvin being the only scale that avoids using zero values, right? Using negative values, I'm sorry. Fahrenheit, though, on the other hand, right, note that there are way more than 100 degrees here, right? Which means that the size of a Fahrenheit degree is smaller, yes? The size of a Fahrenheit degree is smaller, right? Which is why that conversion is more thoughtful, yeah? All right. Heat versus temp, super important, and it's a weird concept to wrap your head around, but it is important. So let's go ahead and talk about what's happening here. So here we have, let's say, two boxes, right? And the size of the arrow represents the speed at which that particle is moving, right? So here we have faster moving particles, right? Which if we had a thermometer in here, and if we had another thermometer here, right? What it would say is that this is a higher temperature, and this is a lower temperature, right? Because temperature has to do with the kinetic energy of the respective particles, right? These particles are moving slower, less kinetic energy, lower temperature. These particles are moving faster, more kinetic energy, higher temperature, okay? Now, if I were to open up the boxes, right, such that these things were to intermingle, right, then what would happen is this faster moving particle would then run into that particle, and as they collide, some of the energy from here would be transferred to this one, and the pink particle would have a little more energy, which means that, right, temperature would go up a little bit. This particle would have a little less energy, so its temperature would go down a little bit, right? And over the millions of collisions that would happen between all the particles, right, eventually we reach thermal equilibrium, just like we were talking about with that cup of ice water, right, where heat, right, is the total amount of energy or joules that are exchanged over the course of all those collisions, right, where temperature just allows us to say these are faster particles, these are slower particles, right, and we can see, right, when we reach thermal equilibrium, because then there will be no further change in the temperature. Yes? Good? All right, which then brings us to some more conversions where we're just converting using the Celsius, Kelvin, and Fahrenheit scales. And so we're just going to use our equations, right?
Aluminium, silicon, phosphorus, then sulfur, chlorine, and argon, potassium, and calcium, so you'll grow strong, scandium, titanium, vanadium, and chromium, and manganese. This is the periodic table.
All right. Thank you for listening. Be good, and I will see you soon. Bye.